There is a planet in our solar system that we have visited exactly once. One spacecraft, one flyby, 6 hours. That was 1986, 38 years ago. Since then, no orbiter, no probe, no atmospheric descent vehicle, nothing. We have sent spacecraft to orbit Mars, to orbit Saturn for 13 years, to orbit Jupiter, to land on comets, to fly past Pluto. We have sent rovers to drive across the surface of another world. We have built a space station where humans have lived continuously for over 2 decades. And the 7th planet from the Sun, a world we can see with the naked eye on a clear, dark night, has received one visitor in all of recorded human spaceflight history. 6 hours. The planet is Uranus, and the reason we have not gone back is not, as you might assume, simply a matter of resources or priority or political will. It is something more interesting than that. It is that every time we look at Uranus more carefully, it presents new puzzles that our current models cannot resolve. Every new measurement raises new questions. The planet is not just unexplored. In a meaningful scientific sense, it is not understood. And understanding Uranus turns out to matter enormously, not just for our knowledge of this one world, but for our ability to interpret the most common type of planet in the observable galaxy. Tonight we are going to think carefully about what makes Uranus strange. Not the list of curiosities you find in any encyclopedia entry. The deeper strangeness, the kind that keeps planetary scientists genuinely uncertain after decades of study. If the night is long, stay. Start with the most obvious thing. Uranus is lying on its side. This is not a metaphor. The rotational axis of Uranus is tilted 97.77 degrees relative to its orbital plane. For comparison, Earth is tilted 23.5 degrees. Mars is tilted 25 degrees, Saturn 27. Jupiter barely tilts at all, about 3 degrees, nearly perfectly upright. Uranus rotates almost horizontally. Its poles point roughly in the direction where other planets' equators would be. Think about what this means physically. On Earth, the cycle of seasons occurs because our tilted axis means different hemispheres receive more direct sunlight at different points in our orbit. But Earth's 23.5 degree tilt means no part of the planet is ever completely removed from sunlight for more than a day at a time. Uranus, with its 97.77 degree tilt, creates a fundamentally different situation. Each pole of Uranus receives continuous sunlight for approximately 42 years, and then is plunged into continuous darkness for approximately 42 years. Not days of polar night like Earth's Arctic regions, not weeks, 42 years. Each season on Uranus is longer than a human lifetime. The Uranian year is 84 Earth years. During most of an Uranian orbit, one hemisphere faces the Sun almost continuously, while the other faces away into space. The geometry of illumination on Uranus is unlike anything in the rest of the solar system. When Voyager 2 flew past Uranus in January 1986, it was approaching a specific moment in Uranus's seasonal cycle. The southern pole was pointed almost directly at the Sun. This was not typical. It was one specific configuration out of the full 84-year cycle. And it meant that the encounter gave us data representing one specific seasonal extreme rather than an average condition. We saw Uranus in one season, just one, and we have never been back to see what it looks like in the others. Why does Uranus lie on its side? The textbook answer: something hit it. A protoplanetary body, roughly the size of Earth, struck the forming Uranus at an oblique angle during the chaotic period of early solar system formation and knocked it over. The impact was violent enough to reorient the planet's rotational axis from something more upright into its current near-horizontal orientation. This explanation is physically plausible. Giant impacts were common during the early solar system. The Moon itself was formed from such an impact, a Mars-sized object colliding with the early Earth and blasting debris into orbit. A single large impact could plausibly account for Uranus's axial tilt, and the explanation receives support from an interesting piece of evidence. Uranus's rings and moons orbit in the planet's equatorial plane. If you tilt the planet, you tilt the rings and moons with it. They do. The moons of Uranus orbit in the equatorial plane. That is, they orbit in the same tilted orientation as the planet's rotation. This is consistent with a system reshaped by a single large impact, rather than accumulated by smaller events. So far, plausible. But here is where the first real puzzle appears. If Uranus were struck hard enough to tilt a planet 14 times the mass of Earth, that impact deposited an enormous amount of energy. Heat. A massive impact on a body the size of Uranus would melt and superheat the planet's interior significantly. That heat should still be present. It should be radiating outward into space. Neptune radiates it. Neptune, a planet with nearly the same mass, similar composition, and similar distance from the Sun, emits approximately 2.6 times more energy than it receives from the Sun. Neptune has an internal heat source, and that internal heat drives its atmospheric dynamics. It is why Neptune has some of the fastest winds in the solar system, with measured speeds exceeding 2,000 kilometers per hour, and why it shows complex atmospheric structure, including the Great Dark Spot that Voyager 2 observed. Uranus emits almost no internal heat. Its measured internal heat flux is so close to zero that some measurements have found it consistent with no excess heat at all. The planet receives energy from the Sun and radiates back roughly what it receives, no more. This is called the Uranus heat flow problem, and it is one of the deepest unsolved puzzles in planetary science. Where did the energy from the giant impact go? The most widely discussed hypothesis: there is an insulating layer inside Uranus, some layer of material that prevents internal heat from reaching the outer atmosphere and being radiated away. Perhaps a layer of ice in an unusual crystalline or ionic phase. Perhaps a compositional boundary that creates a thermal barrier. Perhaps some consequence of stratification in the deep interior that suppresses convection. But this explanation immediately raises another question. Why does Neptune not have the same insulating layer? Neptune is compositionally similar to Uranus. The two planets are often discussed as a pair, the ice giants, because they share fundamental properties that distinguish them from the gas giants Jupiter and Saturn. If an insulating layer explains Uranus's anomalously low heat flow, something specific to Uranus's history must have created it. The giant impact is the natural candidate. Perhaps the impact created a specific stratification that Neptune's quieter history did not produce. But the details of how this would work are not established. There is a second version of the impact hypothesis that attempts to address this. Not one impactor, but two. Two successive impacts, the first tilting the planet, the second occurring at a different angle, that somehow set up the internal stratification responsible for the heat flow suppression. Simulations have explored this scenario, and it can reproduce some of Uranus's properties. But it requires two specific impacts with specific parameters, which is harder to justify probabilistically. There is also a hypothesis involving not an impact at all, but early gravitational interaction with a giant planet, Jupiter or Saturn, perturbing Uranus's orbit and spin during a period of orbital instability in the early solar system. This is related to the Nice model of solar system dynamical history, which proposes that the outer planets underwent a period of significant orbital migration and gravitational scattering early in solar system history. The honest assessment: we do not know why Uranus lies on its side, and we especially do not know why it lies on its side while retaining essentially no internal heat. These questions are connected, and both remain genuinely open. This is the first layer of strangeness. Now go deeper into the interior. Uranus and Neptune are classified as ice giants to distinguish them from Jupiter and Saturn, which are gas giants. The term ice giant reflects a real difference in bulk composition. Jupiter and Saturn are dominated by hydrogen and helium, the lightest elements, the primordial gases of the universe. Uranus and Neptune contain substantially more of the heavier elements, oxygen, carbon, nitrogen in compounds like water, methane and ammonia, along with rock and metal. The word ice is misleading when applied to the interiors of these planets. Under the conditions that exist inside Uranus, extreme pressure, high temperature, the compounds we think of as ices on Earth do not exist as frozen solids. They exist in exotic states that are not well understood and are difficult to study experimentally. One of the most striking predicted properties of Uranus's interior is the existence of superionic water. Superionic water is a phase of matter that exists at extreme pressure and temperature. In superionic water, the oxygen atoms form a crystalline lattice. They lock into a regular arrangement like atoms in a solid. But the hydrogen atoms, the protons, are freed from their bonds and move through the oxygen lattice like ions in a liquid. The result is a material that is simultaneously a solid, in terms of its oxygen structure, and a conductor, because the freely moving protons carry charge. Laboratory experiments using high-powered lasers to compress and heat samples of water to extreme conditions have produced evidence consistent with superionic behavior. The pressures required are millions of times atmospheric pressure. The temperatures are thousands of degrees. These conditions exist in the interiors of ice giants. Superionic water has some specific implications. It is a good electrical conductor, which has implications for how magnetic fields are generated inside these planets. It may have unusual density and thermal properties that affect how heat moves, or does not move, through the planet's interior. And it may behave in ways that are fundamentally different from any material we can study readily in a laboratory. We have never directly sampled anything from the interior of Uranus. Everything we believe about its interior is inferred from its bulk properties: mass, radius, gravitational field, surface composition, plus laboratory experiments at high pressure and temperature, and theoretical modeling. The uncertainty in our interior models is large. We do not know precisely where the boundaries between different compositional and phase layers lie. We do not know the exact thermal structure. We do not know whether Uranus has a well-defined rocky core or whether the rocky material is distributed through the interior. We do not know whether superionic water layers exist at the depths where conditions are right for them, or whether some other phase structure is present. Interior models of Uranus are models, educated inferences, not direct knowledge. This would be true of any planet we cannot sample directly. What makes Uranus specifically notable is how poorly we can constrain its interior model compared to other planets. We have seismic data from Earth. We have returned samples from the Moon. We have gravity mapping of Mars. We have atmospheric probes that descended into Jupiter. For Uranus, one flyby, no atmospheric probe, no orbital gravity mapping campaign, no seismic network. The foundation of our interior models is far weaker than for almost any other body we have studied substantially. Now go to the magnetic field. Planetary magnetic fields are generated by the circulation of electrically conducting fluid in a planet's interior. Earth's magnetic field is produced by circulation in its liquid iron outer core, a process called the geodynamo. Jupiter and Saturn have magnetic fields generated by circulating metallic hydrogen deep in their interiors. The character of the resulting magnetic field depends on the geometry of the conducting region and the dynamics of fluid motion within it. A single dominant convecting region deep in a planet tends to produce a dipole field, the field of a bar magnet, with two poles and a relatively simple structure oriented roughly along the rotation axis. Earth's magnetic field is a somewhat tilted dipole. The magnetic axis is offset from the rotation axis by about 11 degrees. Jupiter and Saturn have broadly dipolar fields as well. Uranus does not have a dipolar magnetic field. Uranus's magnetic field is tilted 59 degrees away from the rotation axis. And it is not centered on the planet's center. The field is offset, shifted from the geometric center of Uranus by approximately 1/3 of the planet's radius. This is not a subtle difference. A 59-degree offset and a substantial displacement from center together produce a magnetic field geometry that looks nothing like the relatively tidy fields of the gas giants. The magnetic field of Uranus is geometrically complex. It has significant non-dipole components, meaning significant contributions from quadrupole and higher-order terms in the mathematical description of the field. Neptune has a similarly strange magnetic field, offset from center and tilted about 47 degrees from the rotation axis. The fact that both ice giants have similarly unusual magnetic fields suggests that this is not an accident or an extreme outlier. It is a systematic property of the ice giant class. The leading explanation? The dynamo generating the magnetic field is not located deep in the planet's core, as in Earth, Jupiter, and Saturn. Instead, it is located in a relatively shallow layer, perhaps a layer of superionic water or ionic fluid at intermediate depths. This shallower, more extended dynamo region produces a more complex field with larger contributions from higher-order terms, consistent with what we observe. This explanation is physically motivated and broadly consistent with theoretical understanding of how dynamos work, but it has not been directly confirmed. We cannot directly observe the dynamics of fluid motion inside Uranus. The explanation is inferred from what we observe at the surface and from models of the interior. And the explanation raises its own question. Why does the conducting layer sit where it does? What determines its depth and extent? How does it relate to the compositional and phase structure of the interior? These questions connect back to everything we do not know about the interior. The magnetic field of Uranus is one of the most complex of any planet in the solar system. It is arguably the least understood major planetary magnetic field. And understanding it requires understanding the interior, which we do not. Now think about the atmosphere. When Voyager 2 flew past Uranus in January 1986, the images it returned were striking for a specific reason. There was almost nothing to see. A featureless pale blue-green disk. No bands, no storms, no obvious cloud structure, no great red spot analogue. The most visually dramatic feature of Uranus's atmosphere was its lack of features. This was a puzzle. Jupiter and Saturn are visually spectacular, banded, stormy, dynamically complex atmospheres driven partly by their enormous internal heat sources. Neptune, despite being nearly identical to Uranus in composition and size, showed the great dark spot, active cloud systems, and some of the most extreme winds measured anywhere in the solar system. Uranus in 1986 looked like a billiard ball. The leading explanation connects back to the heat flow problem. The atmospheric dynamics of gas and ice giants are driven partly by their internal heat. Rising plumes of warm gas from the interior disrupt the atmosphere, drive convection, create the banded structure visible on Jupiter and Saturn. Without a significant internal heat source, as Uranus apparently lacks, the atmosphere is more sluggish, more stable, less dynamically active. But here is what complicates this picture considerably. Uranus is not always quiet. As Uranus has moved through its long orbit since the Voyager encounter, seasonal changes have progressed. The planet is no longer in the same extreme southern pole-facing configuration it was in 1986. Hubble Space Telescope observations have shown dramatic changes in Uranus's atmosphere in the decades since Voyager. Large, bright storms, active cloud features, complex structure in the upper atmosphere. Uranus in 2006, when it was near equinox, with both hemispheres receiving roughly equal sunlight, showed storms and cloud features far more dramatic than the blank sphere Voyager photographed, and observations closer to the present show ongoing atmospheric activity. This means that the 1986 Voyager flyby captured Uranus during a particularly quiet phase of its 84-year seasonal cycle. The bland appearance was real, but it was not the full story. Uranus's atmosphere is seasonally variable in ways we have only begun to observe across a fraction of one complete orbital period. We have never observed Uranus across a full year. We have sampled roughly half of one orbital cycle with any degree of systematic coverage. The full character of Uranian atmospheric variability is unknown. What drives the storms that do appear? How does the deep atmospheric circulation relate to what we observe at cloud top level? What does the weather look like in the deep atmosphere below the visible cloud decks? None of these questions can be answered with current data. An atmospheric probe, a vehicle that descends into Uranus's atmosphere, measuring composition, temperature, pressure, and wind velocity at each altitude until it is crushed by pressure, would transform our understanding the way the Galileo probe transformed our understanding of Jupiter's atmosphere in 1995. The Galileo probe descended into Jupiter for about an hour before being destroyed, and in that hour it revolutionized our understanding of Jovian atmospheric composition, finding that Jupiter is far more enriched in heavy elements than solar composition models predicted, and that the elemental ratios differ from what had been assumed. An analogous measurement at Uranus would answer some of the most fundamental questions about how ice giants form, what materials they accreted, what the temperature profile was in the protoplanetary disk at Uranus's formation location, how its composition compares to models of the outer solar system. That probe has never been sent. Now think about the rings. Uranus has rings, 13 known rings, all discovered after Voyager 2 or by Voyager itself. The planet's rings were not known from Earth-based observation before 1977, when they were serendipitously detected during a stellar occultation. The rings of Uranus are strikingly different from Saturn's rings. Saturn's rings are wide, bright, and made of highly reflective water ice, among the most visually prominent features of any planet in the solar system. Uranus's rings are narrow and extraordinarily dark. The main rings have an albedo, a reflectivity, of less than about 10%. They absorb light rather than reflecting it. They are nearly as dark as coal. What are they made of? We do not know with precision. Spectroscopic data from Voyager was limited. The rings were compositionally characterized in broad terms: dark material, possibly carbon-rich, possibly processed by radiation from the charged particle environment of Uranus's magnetosphere. But the detailed composition remains unconstrained. James Webb Space Telescope observations of Uranus in 2023 provided dramatically better data on the ring system than any previous observation. JWST imaged the rings in the infrared with spatial resolution and sensitivity far beyond what previous telescopes achieved. One of the interesting findings from JWST data: the inner epsilon ring emits thermally. It is warmer than expected given its darkness. A dark object in space should be cold because it absorbs most incoming radiation without efficiently re-radiating it. The fact that the epsilon ring emits more thermally than models predicted suggests either that the material has unusual thermal properties, or that there is some heating mechanism not captured in simple models, or that the composition is different from what has been assumed. This is a new puzzle created by better observations. This is characteristic of Uranus as a scientific object. Every time we look at it with better instruments, we find new puzzles rather than resolving old ones. The planet does not yield to improved observation in the way that planets that match our models do. It reveals new complexity. Now turn to the Moon system. Uranus has 27 known moons, named, uniquely in the solar system, after characters from Shakespeare and Alexander Pope, rather than from classical mythology. The 5 largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. Miranda is the most geologically interesting body in the Uranian system, and possibly one of the most geologically puzzling objects in the solar system. Miranda is small, about 470 kilometers in diameter, smaller than Saturn's moon Mimas, smaller than many asteroids. By the logic of planetary geology, Miranda should be a geologically dead, heavily cratered ice ball. Objects this small cool rapidly after formation. They have little radioactive heating. The only other significant heat source would be tidal flexing from gravitational interaction with Uranus, but Miranda's current orbital configuration does not produce significant tidal heating. Miranda's surface should be boring, monotonously cratered, old, undisturbed. Miranda's surface is one of the most geologically bizarre landscapes in the solar system. It has enormous canyon systems, some of the deepest in the solar system relative to the body's size. It has Verona Rupes, an escarpment that stands approximately 20 kilometers high. That is nearly 4 times the height of Everest above sea level on a world only 470 kilometers across. If you were standing on the rim of Verona Rupes and dropped a rock over the edge, it would take approximately 10 minutes to reach the bottom, because Miranda's gravity is so low that the rock would fall in slow motion. It has chaotic terrain, a region called the coronae, which shows concentric ridges and valleys in a pattern that looks nothing like any simple geological process. The coronae have been variously explained as the result of past partial melting, as ancient upwellings of material from the interior, as the aftermath of tidal heating during a different orbital resonance in the past. There is another hypothesis. Miranda was hit by an impactor that completely shattered it, and the pieces reaccreted under gravity in a somewhat scrambled order. The chaotic surface would then represent a world that was literally broken apart and put back together wrong. The problem is that none of these explanations is clearly established. The data from Voyager 2, while revealing Miranda's surface in broad strokes, was obtained during a single flyby at resolution too limited to test specific geological hypotheses definitively. Voyager 2's closest approach to Miranda was about 29,000 kilometers, which was actually the best coverage of any Uranian moon during the flyby, but it still left enormous ambiguity about the detailed geology. Miranda is one of the most scientifically interesting bodies in the outer solar system precisely because it should not look the way it looks. Something happened to it. We have inadequate data to determine what. Now think about something more recent that has significantly elevated the scientific priority of a Uranus mission. The discovery that the larger moons of Uranus may harbour subsurface liquid water oceans. A study published in 2023 reanalyzed Voyager 2 data and applied modern thermal models to the 4 largest Uranian moons, Ariel, Umbriel, Titania, and Oberon. The finding: based on the energy budget and internal heating rates from radiogenic decay, these moons may be warm enough in their interiors to maintain liquid water layers beneath their icy surfaces. This is not confirmed. It is an inference from modelling and reanalysis of old data, but the implication is significant. Europa, Jupiter's moon, is the iconic subsurface ocean world, with an ice-covered liquid water ocean potentially 100 kilometers deep. Europa Clipper, launched in 2024, is on its way to characterize Europa's ocean and assess its habitability. The intense focus on Europa comes from the understanding that liquid water plus chemical energy plus time might equal life. If Ariel, Umbriel, Titania, and Oberon harbour subsurface oceans, then the Uranian system contains potentially 4 ocean worlds, in addition to whatever lies beneath Miranda's chaotic surface. That would make the Uranian system arguably the richest concentration of potentially habitable environments in the outer solar system, more than the Jovian system, more than the Saturnian system. We would not know this from any observations we have made. We would know it because better thermal models applied to 38-year-old Voyager data suggested it as a possibility. What would actually confirming or refuting these subsurface oceans require? An orbital mission. Magnetometric measurements that can detect the induced magnetic fields produced by conducting liquid layers beneath icy surfaces, the same technique used to infer Europa's ocean. Gravity measurements that can constrain interior density structure. Infrared spectroscopy that can characterize the composition of surface materials that might be emplaced from the interior. All of this requires not a flyby, but an orbiter spending years in the Uranian system. we have not sent one. Now think about why, and what understanding Uranus means beyond this single planetary system. The Kepler Space Telescope, operating from 2009 to 2018, surveyed approximately 150,000 stars and discovered thousands of confirmed exoplanets. The statistical analysis of those discoveries produced one of the most significant and surprising results in the history of planetary science. The most common type of planet in our galaxy, by a substantial margin, is a planet with a radius somewhere between 1.5 and 3.5 times Earth's radius. These planets are called mini-Neptunes or sub-Neptunes. They are larger than Earth, but significantly smaller than Neptune. They orbit at various distances from their host stars, and they are found around stars of various types. In our solar system, there are no planets in this size range. We have Earth and Venus and Mars, all smaller. We have Uranus and Neptune, larger. The size range that appears to be the most cosmically common corresponds to no planet we can study directly, or nearly no planet. Uranus, with a radius of about 4 Earth radii, and Neptune, with a similar radius, are the closest analogues in our solar system to the mini-Neptune population. They are bigger than most mini-Neptunes, but they share a fundamental property that distinguishes them from gas giants. Their bulk composition is dominated by heavy elements, water, rock, carbon compounds, rather than by hydrogen and helium. This compositional difference matters enormously for understanding how planets of this class form, evolve, and behave. What is the internal structure of a mini-Neptune? How thick is its atmosphere? Does it have a rocky core? Does it have a liquid water layer? How does its heat flow work? How does its magnetic field form? All of these questions are constrained by having a physical example of the ice giant class that we can study in detail. Uranus is that example. It is the closest ice giant, the most accessible representative of the most common type of planet in the galaxy. When JWST observes the atmosphere of a mini-Neptune orbiting another star, and JWST is doing this, characterizing the atmospheres of exoplanets with unprecedented spectroscopic detail, the interpretation of those observations depends on having good models for how planets of this composition behave. Those models need ground truth. Ground truth requires detailed study of a real ice giant. In 2023, the Planetary Science Decadal Survey, the document produced every 10 years by the National Academies of Sciences that synthesizes the scientific community's priorities for NASA, ranked a flagship mission to Uranus as its top priority among all planetary science missions. Above Mars, above Europa, above anything else. Top priority. This was not a sentimental choice. It was a judgment by the scientific community that the gap in our understanding of the ice giant class is the most consequential gap in planetary science for interpreting the broader universe, and that addressing it requires an orbital mission to Uranus. The proposed mission, the Uranus Orbiter and Probe, would include a spacecraft in orbit around Uranus for multiple years, systematically mapping the planet's gravity, magnetic field, atmospheric composition, and ring and moon system, and an atmospheric probe that would descend into Uranus's atmosphere, measuring composition and temperature and pressure until pressure destroys it, returning the kind of direct compositional data that no amount of remote observation can provide. The recommended launch window is approximately 2031 to 2038. An appropriate planetary geometry for efficiently reaching Uranus with a gravity assist from Jupiter occurs during this period. If the window is missed, the next comparable opportunity is more than a decade away. As of now, the mission has been recommended but not funded. The difference between a recommendation and a funded mission is substantial. It requires sustained political and budgetary commitment that has not yet been secured. Now think about what JWST has already shown us about Uranus. Because the telescope's observations represent the most detailed view of the planet we have had since Voyager, JWST observed Uranus in 2022 and 2023, producing images of extraordinary quality. The infrared capabilities of JWST reveal features in Uranus's atmosphere that are invisible in visible light. The observations showed the planet's polar cap, a region of enhanced brightness at the North Pole that has been growing as Uranus's northern hemisphere enters its long summer, with structural detail never before resolved. JWST also imaged the rings with sensitivity that revealed their thermal emission. The discovery that the epsilon ring emits more thermally than expected was one of the early results from these observations. It suggests that the ring material has different thermal properties than simple models assumed. JWST's observations also revealed stratospheric structure, atmospheric layers above the main cloud decks, in greater detail than previous observations. The Uranian atmosphere has a complex vertical structure with multiple distinct layers, and JWST's infrared spectroscopy can probe different depths depending on the wavelength observed. Every JWST observation of Uranus adds information, and every new piece of information reveals more about what we do not know. The planet does not simplify as we look harder. Now think about what observations from Earth, the Vera C. Rubin Observatory, will add to understanding the outer solar system context in which Uranus exists. The Vera C. Rubin Observatory began science operations in 2024. Its legacy survey of space and time is a decade-long program mapping the entire visible sky every few nights, going far deeper than any previous survey. For outer solar system science, Rubin will discover trans-Neptunian objects, small bodies in the Kuiper belt and beyond, in numbers that dwarf all previous surveys. Current estimates. From the current catalogue of a few thousand known trans-Neptunian objects, Rubin will expand this to hundreds of thousands. This matters for understanding Uranus in context because the distribution and orbital properties of trans-Neptunian objects record the history of the outer solar system's dynamical evolution, including the history of Uranus and Neptune's migration and their role in sculpting the outer solar system. The orbital structure of the Kuiper belt, which families of objects exist, what orbital resonances they occupy, how many objects are in each population, encodes information about how Neptune migrated outward and how it scattered material during that migration. Better constraints on this structure from Rubin data will improve our understanding of the dynamical history that put Uranus and Neptune where they are and gave them the properties they have. Additionally, Rubin will test the Planet 9 hypothesis, the idea that a large, undiscovered planet in the outer solar system is responsible for the clustering of trans-Neptunian object orbits observed in the current catalogue. If Planet 9 exists, Rubin should either confirm or significantly strengthen its statistical signature as the catalogue of trans-Neptunian objects grows. If Planet 9 does not exist, Rubin's expanded catalogue should dissolve the apparent clustering into statistical noise from a small sample. Either outcome advances understanding of what is out there beyond Neptune. The connection to Uranus. If Planet 9 exists, understanding why it is where it is, what dynamical history placed a large planet in a remote, highly inclined orbit, feeds back into models of the early solar system's dynamical history, including the events that tilted Uranus and gave it its current properties. The outer solar system is a connected system. Every piece of evidence constrains the whole. Now think about something that is often mentioned briefly but deserves more serious consideration: the specific challenge of communicating with a spacecraft at Uranus. Uranus is currently approximately 19 to 20 astronomical units from Earth, depending on orbital positions. One astronomical unit is the Earth-Sun distance, about 150 million kilometers. Uranus is roughly 2.7 to 3 billion kilometers from Earth. At the speed of light, a radio signal takes between 2.5 and 2.7 hours to travel from Earth to Uranus one way. A command sent to an orbiting spacecraft and the acknowledgement that the command was received takes between 5 and 6 hours of round-trip time. This is qualitatively different from operating a spacecraft in Earth orbit or even at Mars, where signal delays are minutes. For a Uranian orbiter, mission controllers cannot respond to developing situations in anything like real time. The spacecraft must be substantially more autonomous, capable of detecting anomalous situations and taking appropriate action before a signal can reach Earth and a response can return. This places requirements on spacecraft design and flight software that are more demanding than for inner solar system missions. The spacecraft must be robust, must have sophisticated fault protection, and must be designed to operate through complex orbital maneuvers and scientific observations without constant human oversight. It also means that the science planning for a Uranian orbiter must be done differently from missions where scientists can respond quickly to data. Observation sequences must be planned in advance, uplinked in batches, and executed autonomously. The spacecraft must have enough onboard memory to store data acquired during periods when transmission to Earth is not occurring. These are engineering challenges, not fundamental physical barriers. They have been managed before. Cassini at Saturn operated at similar distances with similar communication constraints, and it was one of the most scientifically productive planetary missions ever flown. But they add complexity and cost to the mission design. Now think about one more dimension of Uranus's strangeness: the diamond rain. In the interior of Uranus, where temperatures are tens of thousands of degrees and pressures are millions of times Earth's atmospheric pressure, methane, CH4, can decompose. The carbon atoms released from methane can be subjected to conditions extreme enough to crystallize into diamond. These diamonds, crystals denser than the surrounding material, would sink through the interior. As they fall toward higher pressure regions, they might eventually melt. Some calculations suggest that Uranus may contain liquid diamond oceans deep in its interior, with diamond icebergs floating in them. This was initially a theoretical prediction, but in 2017, an experiment at Stanford provided direct evidence for the process. A laser-driven compression experiment subjected polystyrene, a carbon-hydrogen compound, to pressures and temperatures similar to those in ice giant interiors. Diamond nanocrystals formed. The experiment confirmed that the physical process works. The scale inside Uranus is vastly larger. Estimates suggest that the planet may be producing thousands of tons of diamonds per year. These diamonds are entirely inaccessible. No engineering we can currently conceive would allow recovery of material from Uranus's deep interior. But the diamond rain is not just a curiosity. The formation and sedimentation of diamond in the interior affects the planet's density structure, its thermal profile, and potentially its magnetic field generation. Understanding this process is part of understanding the planet's bulk behavior, and there is no way to directly confirm or measure the diamond rain from outside the planet. It is inferred from theory and laboratory experiments. An atmospheric probe would not reach diamond rain depths. Even an ideal future mission cannot directly observe what happens in Uranus's deep interior. Some aspects of Uranus's strangeness may be permanently inaccessible to direct measurement. We will understand them through inference, modeling, and experiments that simulate the conditions, not through direct observation. This is the situation with many of the most fundamental questions in planetary science. We work with inference and model testing rather than direct observation. But better data from an orbiter, from an atmospheric probe, from improved spectroscopy, narrows the range of viable models and increases the confidence of our inferences. What we know about Uranus is built on a foundation of sparse 38-year-old Voyager data, ground-based and space telescope observations, and theoretical models calibrated against other planets that may be significantly different in their details. Uranus lies on its side. Why is not established. Uranus emits almost no internal heat. Why is not established. Uranus has a geometrically complex magnetic field generated by an unusual dynamo. The details are not established. Uranus may have 4 subsurface ocean moons. Whether this is true is not established. The composition of Uranus's rings, not well established. The detailed vertical structure of Uranus's atmosphere and how it varies seasonally, not established. What happened to Miranda, not established. This list is not a failure of planetary science. It is an accurate picture of the current state of knowledge, accumulated from one flyby and decades of external observation of a planet 19 astronomical units away. The gap between what we know and what we need to know to understand this planet is enormous. And filling that gap matters, not just for Uranus, but for our ability to understand the most common type of planet in the observable universe. That pale blue-green disk is sitting out there, 2.7 billion kilometers away, tilted sideways, cold inside, wrapped in its dark, narrow rings, attended by its geologically baffling moons. We have visited it once, for 6 hours, and we have not been back. Let us now think carefully about what it actually means, concretely, physically, scientifically, that Uranus has been visited once for 6 hours, 38 years ago. Voyager 2 was launched in August 1977. It was designed for the Grand Tour, a rare planetary alignment that allowed a single spacecraft, using gravity assists, to visit Jupiter, Saturn, Uranus and Neptune in sequence. The alignment that made this possible occurs roughly once every 175 years. The last time it occurred, the American Revolution had just begun. Voyager 2 reached Jupiter in 1979, Saturn in 1981. It arrived at Uranus in January 1986. The encounter geometry was unfortunate for science. Because Uranus was oriented with its south pole facing the Sun during the flyby, and therefore facing the incoming spacecraft, Voyager approached Uranus essentially end-on. The planet's rotational axis pointed almost directly toward the spacecraft during the encounter. This meant that mapping the planet's atmospheric dynamics was severely compromised. The rings appeared nearly circular from this angle, rather than showing their full structure. The moons were not well distributed around the planet for a systematic survey. Many of them were clustered in the region Voyager could observe. The encounter lasted 5 hours and 59 minutes of closest approach science. The spacecraft was moving at approximately 16 kilometers per second relative to Uranus. It could not slow down. It could not orbit. It could not return. In those 6 hours, Voyager 2's instruments measured what they could. The magnetic field instruments detected and mapped the bizarre, offset, tilted magnetic field. The planetary radio astronomy instrument detected radio emissions from the magnetosphere. The ultraviolet spectrometer measured the composition of the upper atmosphere. The photopolarimeter system attempted to measure atmospheric properties. The imaging science system returned photographs. And then Voyager 2 was past Uranus on its way to Neptune. The data returned was genuinely valuable. It established that Uranus has an unusual magnetic field, characterized the gross properties of the ring system, discovered 10 new moons, and provided the first close-up images of the 5 major moons. It was a landmark achievement of 1970s and 1980s spacecraft engineering. But the limitations are staggering in retrospect. The imaging resolution of Voyager's cameras, the sensitivity of its spectrometers, the capacity of its data transmission system, all of these were constrained by the technology of the 1970s. The total data volume returned from the Uranus encounter was modest by modern standards. The imaging of Miranda's surface covered a small fraction of the total surface area. The atmospheric measurements probed only the topmost layers. Compare this to what we have done at other planets since. Cassini arrived at Saturn in 2004 and orbited for 13 years until 2017. It made 294 orbits of Saturn. It executed 127 targeted flybys of Titan alone. It mapped Titan's surface using radar, because Titan's thick atmosphere is opaque to visible light, revealing river systems, lakes of liquid methane, and dune fields. It discovered active geysers erupting from Enceladus and flew through those geysers, directly sampling the material from beneath the ice. It measured Saturn's magnetic field in extraordinary detail over years of continuous observation. It deployed the Huygens probe, which descended through Titan's atmosphere for 2 hours and 27 minutes before landing on the surface and continuing to transmit for over an hour. 13 years versus 6 hours. The Mars Reconnaissance Orbiter has been mapping Mars from orbit since 2006, nearly 2 decades of systematic observation. The MAVEN mission has been studying Mars's atmosphere and its interaction with the solar wind since 2014. The Curiosity rover has been driving across the Martian surface since 2012, drilling into rocks, measuring atmospheric composition, characterizing the geology of Gale Crater with a level of detail that would have seemed inconceivable to planetary scientists of the Voyager era. Juno has been orbiting Jupiter since 2016, measuring Jupiter's gravitational field with enough precision to constrain the planet's deep interior structure, including the extent of the metallic hydrogen layer and the possible existence of a diffuse rocky core rather than a compact one. Juno's microwave radiometer has probed the ammonia distribution in Jupiter's atmosphere to depths of hundreds of kilometers below the cloud tops. These are the kinds of measurements that transform understanding. Not a snapshot, but a systematic survey. Not 6 hours, but years. Not one instrument configuration, but comprehensive multi-instrument coverage, optimized for the specific scientific questions being asked. Uranus has none of this. Everything we know about Uranus's interior comes from inference rather than direct measurement. The gravity field was measured during the brief Voyager flyby with limited precision.
We do not have the orbital coverage needed to separate different contributions to the gravity field and determine the density structure of the interior with confidence. Models of Uranus's interior span a wide range of possibilities, some with a compact rocky core, some with diffuse heavy elements distributed throughout the interior, some with stratified fluid layers, some without. The data cannot distinguish between them. The atmosphere has been observed externally from telescopes, Hubble, Keck, Gemini, JWST, but external observation cannot probe below the visible cloud layers. The composition of the deep atmosphere, where the answers to Uranus's formation history are recorded, is inaccessible without an atmospheric probe. The magnetic field was characterized during 6 hours of flyby. We have no information about how it varies over time, whether it fluctuates like Earth's magnetic field, whether it shows seasonal variations related to the planet's unusual orientation, whether it has reversed polarity in the geologically recent past. We have a single snapshot of a complex, dynamic system. Now think about what the Uranus orbiter and probe would actually do, concretely, observation by observation, if it is eventually funded and launched. The mission, as currently envisioned, would launch in the 2031 to 2038 window, reach Uranus approximately 13 years after launch, and then spend at least 4 years in orbit. Some mission concepts extend the orbital phase to 7 or more years. The arrival phase would begin with orbital insertion, a burn to slow the spacecraft and allow Uranus's gravity to capture it into orbit. This is the most critical moment of the mission. A failure of the insertion burn means flying past Uranus without capturing, losing the mission entirely. The insertion burn must work on the first attempt, without real-time correction from Earth due to the communication delay. Once in orbit, the spacecraft would begin its systematic survey. Gravity science would be a primary objective throughout the mission. By tracking the spacecraft's orbit with extreme precision, measuring tiny accelerations caused by gravity field variations, scientists can map the internal density structure of Uranus. The technique is the same one Juno uses at Jupiter and the same one the Grail mission used to map the Moon's gravity field in extraordinary detail. Multiple orbits at different inclinations are needed to fully characterize the three-dimensional gravity field. This takes years. The magnetic field would be measured continuously throughout the mission. Multiple years of magnetic field data would reveal whether the field varies with time, characterize its full complexity in 3 dimensions, and allow analysis of the relationship between the magnetic field structure and the internal dynamics generating it. We would finally have data to test theoretical models of ice giant dynamos, rather than constraining them with a single 6-hour encounter. Atmospheric science would be a continuous focus. The orbiter's instruments would probe the atmosphere at multiple wavelengths, building up a picture of the atmospheric structure, composition, and dynamics across seasons and latitudes. Over years of observation, the seasonal evolution of the atmosphere would be tracked in real time, something never possible before. The ring system would be systematically characterized. Stellar occultations, moments when the spacecraft can watch a star pass behind the rings, would reveal the ring's detailed structure with precision far beyond what ground-based or Hubble observations can achieve. The composition of ring material would be characterized through spectroscopy from multiple viewing geometries. Multiple flybys of the major moons would build up global coverage of their surfaces. Miranda's geology could be mapped at scales that reveal whether the coronae are impact scars or tectonic features or ancient upwellings or something else. Ariel's relatively young-looking surface, it has fewer craters than Umbriel or Oberon, suggesting more recent geological activity, could be characterized in detail. The subsurface ocean hypothesis could be tested through magnetic field measurements at close range. And then there is the atmospheric probe. The probe would separate from the orbiter sometime before the mission's planned entry into the atmosphere, weeks or months depending on the mission architecture. It would enter the atmosphere at high velocity, decelerating through aerodynamic braking. After the deceleration phase, a parachute would deploy, slowing the probe for its scientific descent through the atmosphere. During the descent, which would last somewhere between 30 minutes and a few hours depending on the depth targeted, the probe would measure temperature as a function of altitude. This reveals the thermal structure of the atmosphere, where it heats and where it cools, and what that implies about energy sources and dynamics. Pressure as a function of altitude. Combined with temperature, this gives the atmospheric density structure and allows comparison with models. Wind velocity. Doppler tracking of the probe's radio signal reveals its horizontal velocity relative to the planet, giving direct measurement of wind speed and direction at each altitude. Atmospheric composition. Mass spectrometry would measure the abundance of every major molecule: hydrogen, helium, water, methane, ammonia, and their isotopes. The isotopic ratios of key elements are particularly valuable because they are signatures of the planet's formation conditions. The noble gas abundances, helium, neon, argon, krypton, xenon, are especially important. Noble gases do not react chemically. They were incorporated into the planet during formation and have not been modified by chemistry since. Their abundances relative to hydrogen record the conditions in the protoplanetary disk where Uranus formed, particularly the temperature at Uranus's formation location, because different noble gases condense from the gas phase at different temperatures. Measuring the noble gas profile at Uranus is one of the highest priority measurements in planetary science. The Galileo probe at Jupiter measured noble gases at Jupiter in 1995, producing a result that was immediately puzzling and has driven theoretical work for 30 years since. Jupiter's noble gases are enriched relative to the Sun, but in a pattern that is hard to explain by any simple formation model. Understanding how Uranus's noble gas pattern compares to Jupiter's would dramatically constrain models of how both planets formed. The probe would eventually stop transmitting, either because it runs out of battery power or because the atmospheric pressure becomes too great for the electronics to survive, or both. This happens somewhere between a few tens and a few hundreds of kilometers below the visible cloud tops, depending on the probe's design and the internal structure of the atmosphere. After the probe falls silent, the orbiter, having received and stored the probe data, would relay the complete dataset back to Earth. The analysis of that dataset would take years. It would be a scientific resource mined for decades, the way the Galileo probe data has been analysed and reanalyzed for 30 years.
And it would tell us things about how Uranus formed, what it is made of, and how ice giants in general behave that no amount of external observation can provide. Now let us think about what the science would mean beyond Uranus itself. The significance of a Uranus mission extends far beyond our solar system because of the exoplanet connection. When astronomers observe a mini Neptune orbiting another star using JWST, they see a dip in the star's light during transit, giving the planet's radius, a spectroscopic signal of molecular absorption in the atmosphere, giving some compositional information.
In favourable cases, a radial velocity measurement giving the planet's mass. From these observables, they want to infer, what is this planet made of? How did it form? Is it habitable? What will it look like in 1 billion years? Making these inferences requires a physical model, a theory of how planets of this size and composition work. How does the interior structure depend on the bulk composition? How does the atmosphere relate to the interior? How does the thermal evolution proceed over billions of years? The models currently used for these inferences are calibrated primarily against gas giants, Jupiter and Saturn, which are well studied. But gas giants and ice giants are fundamentally different in composition. Applying gas giant models to mini Neptunes introduces errors that are hard to quantify, because we don't have a well-understood ice giant to calibrate against. Uranus is that calibration point.
It is a real ice giant, close enough to study in detail, with known bulk properties and, after a mission, with measured interior structure, atmospheric composition, and magnetic field dynamics. It is the Rosetta Stone for interpreting the ice giant class of exoplanets. The comparison is not hypothetical. JWST has already produced atmospheric spectra of several mini Neptunes. The planet K2-18b, about 2.6 Earth radii, orbiting in the habitable zone of a red dwarf star 120 light-years away, had its atmosphere characterized by JWST in 2023. The spectrum showed methane and carbon dioxide. The interpretation of what this implies about K2-18b's interior structure and potential habitability depends critically on the assumed model for ice giant interiors. Better models, calibrated against a well-studied Uranus, would produce more confident interpretations of K2-18b and every other mini Neptune JWST characterizes. The information flows both ways.
What we learn from JWST about mini Neptune atmospheres informs hypotheses about Uranus that can then be tested by the mission. What the mission reveals about Uranus constrains the interpretation of JWST observations of mini Neptunes. The investigation of Uranus and the investigation of exoplanets are not separate scientific programs. They are parts of the same investigation, requiring different instruments and methods, but answering connected questions about how ice giant planets work. Now think about the timeline problem, and why it matters that the decision to fund a Uranus mission is a decision that must be made now rather than later. The gravity assist window from Jupiter, a trajectory that uses Jupiter's gravity to efficiently bend the spacecraft's path toward Uranus, opens in approximately 2031 and closes in approximately 2038.
Using this trajectory reduces the propellant required to reach Uranus by a significant amount, making the mission significantly cheaper and allowing a heavier spacecraft with more capable instruments. Without a Jupiter gravity assist, reaching Uranus is still possible, but requires either much more propellant, implying a larger, more expensive launch vehicle, or a much longer transit time. Neither is optimal. The last time a comparable Jupiter gravity assist opportunity for a Uranus mission was available, the 1986 launch window, we chose to use Voyager 2 for the Grand Tour, rather than dedicating a mission specifically to Uranus. The result was 6 hours of flyby data. If the 2031 to 2038 window is missed, the next comparable opportunity does not occur for many years. Exactly when depends on the specific trajectory analysis, but estimates range from 1 to 2 decades before a similarly favorable window returns. Planetary missions take approximately a decade from approval to launch. They require years of technology development, instrument building, spacecraft integration, and testing before they can launch. A mission approved today would be hard-pressed to launch even within the 2031 to 2038 window. A mission not yet approved, with no funding and no project team, might very plausibly miss the window. This is the urgency. The Planetary Science Decadal Survey identified the Uranus mission as the top priority and endorsed the 2031 to 2038 launch window. That was in 2023. As of mid-2026, the mission has not been fully funded. The window is shrinking. This is not a situation where technology does not yet exist. The technology needed for a Uranus mission is mature. Spacecraft have operated at similar distances. Atmospheric probes have been built and successfully deployed at Jupiter. Instruments capable of the needed measurements have been developed and flown on other missions. There is no technical barrier. The barrier is organizational and financial. NASA's budget is finite. Multiple high-priority missions compete for funding. Large missions require sustained political commitment across multiple administrations. The time from approval to launch spans the tenure of several different NASA administrators and several different administrations. The history of planetary mission planning is full of missions that were recommended, delayed, revised, and ultimately either drastically descoped or cancelled. The Uranus mission has strong scientific backing. Whether that translates into funded reality depends on factors that go beyond science. Now let us think carefully about something that is not often discussed in the context of Uranus, the question of what the planet sounds like. Not audible sound, space is a vacuum and sound does not propagate, but radio emissions, plasma waves, electromagnetic signals generated by the interaction of charged particles with magnetic fields. Every magnetized planet in the solar system emits radio waves produced by the plasma environment of its magnetosphere. Earth has radio emissions. Jupiter has intense radio emissions, detectable with ground-based antennas before the space age. Saturn has radio emissions. Uranus, despite its unusual magnetic field configuration, also emits. Voyager 2's planetary radio astronomy instrument detected radio emissions from Uranus during the flyby. The emissions were converted to audio frequencies and played as sound, and they are strange. Uranus sounds like a slow, eerie whistling, very different from Jupiter's powerful radio bursts or Saturn's hissing rotational modulation. But we have one 6-hour sample. The radio emissions of Uranus's magnetosphere are dynamic. They depend on the orientation of the planet, which changes seasonally, the interaction with the solar wind, which varies, and processes within the magnetosphere itself. We have no idea how they vary over time, over seasons, over the magnetic field's complex geometry. An orbiter spending years in the Uranian system would continuously monitor radio emissions. That dataset would reveal the dynamics of Uranus's magnetosphere in a way that 6 hours of flyby data cannot begin to. This is one of hundreds of specific scientific measurements that an orbital mission would make that cannot be made from Earth or from a brief flyby. Now let us think about the relationship between Uranus and Neptune, specifically the puzzle of why two planets that are so similar in many respects differ so dramatically in their heat flow and atmospheric activity. The two planets are often described as nearly identical. They have nearly the same mass. Uranus is about 14.5 Earth masses, Neptune about 17 Earth masses. They have nearly the same radius, Uranus about 4 Earth radii, Neptune about 3.9. Their bulk densities are similar. Their compositions, inferred from spectroscopy and density constraints, are similar, ice-dominated interiors with hydrogen-helium envelopes, and yet their behavior is dramatically different. Neptune's internal heat is extraordinary, 2.6 times more energy radiated than received from the Sun. Neptune has some of the fastest winds in the solar system, exceeding 2,000 kilometers per hour. Neptune's atmosphere is visibly active.
the great dark spot that Voyager observed, large-scale storm systems, active dynamics. Uranus emits essentially no excess internal heat. Its atmosphere in 1986 was nearly featureless. Even accounting for seasonal activity, Uranus appears to be a quieter world. What accounts for this difference? The most natural explanation involves their histories. Something happened to Uranus that did not happen to Neptune. Most plausibly, the giant impact that tilted its axis. If the impact created internal stratification that prevents heat from convecting outward, Uranus would retain its heat in the interior, while Neptune, without such stratification, allows heat to escape normally. But this explanation is incomplete. We don't have a quantitative model that successfully predicts Uranus's observed heat flow given a plausible impact scenario. The mechanism by which an impact-created stratification would persist for 4.5 billion years, against the normal tendency of gravitational instabilities to overturn stratification and restore convection, is not clearly established. An alternative explanation involves not the impact directly, but the subsequent evolutionary history. Perhaps Uranus and Neptune both started with similar heat contents. Neptune, for whatever reason, has been able to convect its interior heat outward. Uranus, for whatever reason, has not. The giant impact may have created conditions that have persisted for 4.5 billion years, not because the stratification is inherently stable, but because the timescale for overturning it exceeds the age of the solar system. There is also a less explored possibility. Perhaps Uranus and Neptune are not as similar as we assume, and the similarity is partly a consequence of our limited knowledge. Perhaps their compositions differ in ways that have significant thermal consequences. Without direct compositional measurements of both interiors, we cannot rule this out. Neptune has also been visited only once, also by Voyager 2, also during a brief flyby in 1989. Our knowledge of Neptune's interior is as limited as our knowledge of Uranus's. The comparison between the two planets, which is fundamental to understanding both, is a comparison between two poorly characterized objects. A Uranus mission would dramatically improve the Uranus side of this comparison. A subsequent Neptune mission, there is no funded Neptune mission either, would eventually complete it. Understanding why two nearly identical planets behave so differently is one of the central puzzles in planetary science, and it cannot be solved without substantially better data on both. Now let us think about the specific scientific value of Miranda and why a Uranus orbiter should spend significant time studying this puzzling moon. Miranda is 470 kilometers in diameter. By most metrics, it is an unremarkable small icy moon, but its surface tells a story that does not fit any simple geological narrative. The coronae, three distinct regions named Arden Corona, Elsinore Corona, and Inverness Corona, are each hundreds of kilometers across.
They show concentric patterns of ridges and valleys that are internally consistent but differ markedly from the terrain surrounding them. They look like geological accidents, regions where different processes were operating than in the surrounding areas. The escarpment Verona Rupes is in a class by itself, 20 kilometers tall on a world 470 kilometers across. The ratio of cliff height to body diameter is extraordinary by solar system standards. On Earth, the tallest cliffs are hundreds of meters. On Miranda, a cliff exists that is 20 kilometers high, more than twice the height at which Earth's atmosphere would be below you. Why is Verona Rupes so tall? Several possibilities. Perhaps Miranda experienced tidal heating in the past. If it was in a different orbital resonance than it occupies today, tidal flexing could have generated enough heat to partially melt the interior and drive upwelling.
The upwelling may have created the coronae and the associated topographic extremes. If Miranda then moved out of the resonance, the tidal heating stopped, and what remains is the geological record of a brief, intense episode.
Perhaps Miranda was catastrophically disrupted by a large impact, and the pieces fell back together in a different configuration. This hypothesis has the advantage of explaining the discontinuous surface geology. Different regions represent fragments that happen to reaccrete differently, but it is not clear that a disrupted and reaccreted body would produce the specific structures observed. Perhaps what we see is the consequence of convective overturn in an icy body, regions where warmer ice rose and pushed through the surface, creating the concentric patterns of the coronae and the escarpments associated with them. The problem is that Voyager 2's coverage of Miranda was obtained during a single pass at limited resolution. The coronae were imaged well enough to identify their existence and broad structure, but not well enough to characterize the small-scale features that would distinguish between geological models. The far side of Miranda, the hemisphere away from Voyager's trajectory, was not well imaged at all. A Uranus orbiter conducting multiple close flybys of Miranda over years would build up global, high-resolution coverage. It would allow mapping of the coronae at the scale of individual geological features, hundreds of meters potentially, rather than at the scale of tens of kilometers. It would characterize the interior through gravity measurements at close range. It would measure the magnetic field environment to look for evidence of a conducting liquid layer. Miranda's strangeness may be simply a matter of one unusual period in a small moon's past, or it may reflect something more systematic about how small icy bodies behave. We cannot know without better data, and Miranda is representative of a broader question. All 5 of Uranus's major moons show evidence of geological complexity that exceeds what would be expected for bodies their size. Ariel has a relatively young surface by crater counting standards, suggesting geological resurfacing not long ago in geological terms. Umbriel is mysteriously dark. Its surface reflectivity is lower than can be easily explained by simple models of outer solar system ice chemistry. Titania and Oberon show tectonic features, faults and chasmata that are large enough to record significant geological stress. What drove geological activity in the Uranian moons? The most natural heat source would be tidal interaction with Uranus. If the moons were in resonances in the past, as is suspected, tidal heating could have been substantial. But the current orbital configuration does not produce significant tidal heating for most of the moons. Something changed. Understanding what changed and when is part of the history of the Uranian system. Now let us think about one of the most specific and underappreciated scientific questions about Uranus: the question of how the planet's unusual orientation affects the solar-wind interaction. The solar wind is a continuous flow of charged particles, primarily protons and electrons, from the Sun. Every magnetized planet has a magnetosphere, a region where the planet's magnetic field deflects and traps the solar wind. The shape and dynamics of the magnetosphere depend on the geometry of the magnetic field, the strength of the solar wind, and the orientation of the planet's magnetic axis relative to the solar wind direction. On Earth, the magnetic axis is roughly aligned with the rotation axis, which is roughly perpendicular to the plane of Earth's orbit. The solar wind always approaches Earth from approximately the same direction relative to the magnetic axis. The magnetosphere has a characteristic shape, compressed on the day side facing the Sun, extended into a long magnetotail on the night side, that remains broadly stable over time. Uranus is fundamentally different. Because Uranus's rotation axis points roughly toward the Sun for part of its orbit, and points perpendicular to the Sun direction for other parts, the geometry of the solar wind interaction with Uranus's magnetosphere changes dramatically over the course of one Uranian orbit, 84 Earth years. When Uranus's pole is facing the Sun, as it was during the Voyager encounter in 1986, the solar wind approaches roughly along the rotation axis. The magnetic axis is tilted 59 degrees from the rotation axis. As Uranus rotates on its axis, once every 17.2 hours, the magnetic field tumbles relative to the solar wind direction, completing a full rotation every 17.2 hours. This creates a magnetosphere that is not quasi-static like Earth's. It is a corkscrew, a twisted, rotating magnetic field configuration that the solar wind must interact with as it tumbles. The magnetotail of Uranus is not a simple extended structure like Earth's or Jupiter's. It is a helical structure, wound around the rotation axis as Uranus rotates. The dynamics of this system are exotic and poorly understood. The plasma physics of a rotating magnetic field interacting with the solar wind involves processes that do not occur anywhere else in the solar system in this configuration. The energization of particles, the transport of charged particles within the magnetosphere, the radio emissions generated, all of these depend on the specific geometry that Uranus's unusual orientation creates. We have 6 hours of data on this system. We do not know how it varies over the planet's rotation. We do not know how it varies seasonally. We do not know how it responds to solar wind variations. We have a single snapshot of a dynamically complex system at one specific moment. An orbiting spacecraft spending years in the Uranian system, continuously monitoring the magnetic field, the particle populations and the radio emissions, would accumulate the data needed to understand this exotic magnetospheric configuration. The physics learned would apply not just to Uranus, but to any situation where a magnetic field rotates relative to an external plasma, a configuration that may exist in other planetary systems, including planets orbiting pulsars. Now let us think about the broader context of what we do not know about the outer solar system, the question of what lies beyond Uranus, and what that region of space might contain. In 2016, Konstantin Batygin and Mike Brown of Caltech published a paper arguing that the orbits of several trans-Neptunian objects, bodies in the outer solar system beyond Neptune, are clustered in a way that could be explained by the gravitational influence of an undiscovered large planet. They called this hypothetical body Planet 9. The proposed Planet 9 would have a mass of approximately 5 to 10 Earth masses in the ice giant size range, and would orbit at a distance of 400 to 800 astronomical units from the Sun, with an orbital period of 10,000 to 20,000 years. If Planet 9 exists, it would be the 5th planet beyond Jupiter. It would be in the ice giant size range, and it would be in an orbit so distant and inclined that it has evaded detection in all surveys conducted so far. The existence of Planet 9 remains unconfirmed. Statistical arguments about the clustering of trans-Neptunian object orbits are contested. Some analyses find the clustering is statistically significant, others argue it is an artifact of observational selection effects. Searches of the sky for a slowly moving distant object have not found it. The Vera C. Rubin Observatory's survey will provide the most definitive test of the Planet 9 hypothesis in the next several years. Its unprecedented depth and sky coverage will dramatically expand the catalogue of trans-Neptunian objects, providing a much larger statistical sample for orbit clustering analysis. If Planet 9 exists, Rubin should detect its gravitational signature in the orbital distribution of trans-Neptunian objects, and might directly detect the planet itself. If Planet 9 exists, what is it? One possibility, a planet that formed in the inner solar system and was ejected outward by gravitational interactions with Jupiter or Saturn during the period of dynamical instability in the early solar system. This is the Nice model context again, the same episode of orbital chaos that put Uranus and Neptune in their current orbits may have ejected a 5th giant planet outward. If a 5th planet was ejected from the inner solar system but did not escape entirely, if it was captured into a distant, highly inclined orbit by interactions with the other planets rather than being expelled into interstellar space, it could be sitting in the outer solar system today, unseen, affecting the orbits of trans-Neptunian objects in detectable ways. The existence of such a planet would be a major discovery and would significantly affect our understanding of solar system history. It would also be relevant to Uranus, because the same dynamical episode that ejected a 5th planet may have also been responsible for the encounter that tilted Uranus's axis. Whether Planet 9 exists or not, the outer solar system beyond Neptune contains far more structure than most people appreciate. The Kuiper belt extends from about 30 to 50 astronomical units from the Sun. It contains hundreds of thousands of bodies larger than 100 kilometers in diameter, more than 100 Plutonian analogues in addition to Pluto itself. New Horizons flew past Arakoth, a small Kuiper belt object about 36 kilometers long, in 2019, returning images that revealed a contact binary, two lobes that had gently merged, providing our most direct look at the primordial building blocks of the outer solar system. Beyond the Kuiper belt is the scattered disk, a population of bodies with highly elliptical orbits that take them from near Neptune's orbit out to hundreds of astronomical units. Sedna, discovered in 2003, is the most extreme confirmed example. Its closest approach to the Sun is about 76 astronomical units, its most distant point about 937 astronomical units, and its orbital period about 11,400 years. The origin of Sedna's distant orbit is the subject of ongoing debate. It may reflect the early solar system's birth environment in a stellar cluster. It may be a consequence of Planet 9's gravity, or it may be something else entirely. And beyond all of this is the Oort cloud, the theorized shell of icy bodies extending from roughly 2,000 to 100,000 astronomical units, the source of long-period comets. The Oort cloud has never been directly observed. Its existence is inferred from the orbits of comets that occasionally fall into the inner solar system. But trillions of icy bodies are believed to inhabit this region, representing the outermost debris of the solar system's formation. Uranus sits within this larger context. It is one of the 4 outer planets whose migration and gravitational scattering shaped the entire outer solar system. The Kuiper belt, the scattered disk, the Oort cloud, and possibly the orbit of a 5th planet. Understanding Uranus's current properties and formation history is inseparable from understanding how the outer solar system as a whole came to be. Now let us be specific about what we would need beyond a single Uranus mission to fully understand the ice giant class. A single Uranus orbital mission would dramatically advance our understanding of Uranus specifically. But there are things it cannot tell us. It cannot tell us whether the properties of Uranus are typical of ice giants, or whether Neptune has significantly different interior structure, composition, and dynamics. The comparison between Uranus and Neptune is essential to understanding what is intrinsic to the ice giant class versus what is specific to each planet's particular history. Neptune has been visited once for a few hours in 1989. Everything we said about the inadequacy of Voyager's Uranus data applies equally to Neptune data. A Neptune mission is not currently funded. It was identified as a scientific priority in the Planetary Science Decadal Survey, lower priority than Uranus but high on the list, and there is no concrete plan to fly one. The ice giant class cannot be fully understood from one mission to one planet. The full program requires missions to both. The timelines for such missions, each taking over a decade from approval to arrival, mean that planning must begin soon if both planets are to be visited within scientifically reasonable timeframes. There is also the question of what further missions to Uranus beyond the initial orbiter might accomplish. The UOP, as envisioned, is a flagship mission, large, expensive, comprehensive. But subsequent missions with different objectives could add enormously to what the first mission establishes. A dedicated Uranus atmospheric probe, larger and more capable than the one carried by the UOP, could descend deeper into the atmosphere, reaching pressures where the noble gas abundances can be measured with better precision and where the deep atmospheric circulation can be characterized. A lander on Miranda or Ariel could directly sample the surface and subsurface, measuring composition, age, and geological history in ways that remote sensing from orbit cannot. A Uranus magnetospheric orbiter, optimized for plasma physics rather than geophysics, could characterize the exotic magnetospheric dynamics in detail.
Each of these would build on what the initial mission establishes, but each requires the first mission to have been flown first. We are at the beginning of what could be a sustained program of ice giant exploration that extends decades into the future. Or we are at another moment of delay, like every moment since 1989, when a Uranus follow-up mission could have been planned and was not. The question is whether the scientific understanding of what is at stake, what Uranus represents, what understanding it means for exoplanetary science, what opportunity the current launch window represents, can translate into the sustained commitment that a funded mission requires. The planet is sitting out there, 2.7 billion kilometers away, tilted sideways, silent since 1986. Let us now think about something that rarely enters public discussions of Uranus, what the planet actually looks like from close range, and why that visual experience would be unlike anything a human being has ever seen. When Voyager 2 transmitted its images of Uranus in January 1986, the scientific community was genuinely taken aback, not by what it saw, but by what it did not see. A pale blue-green sphere with almost no visible features, no banding, no storms. A colour so uniform that Voyager's imaging team had to significantly enhance the contrast to reveal even subtle atmospheric structure. The colour itself is worth understanding. Uranus is blue-green because of methane in its upper atmosphere. Methane absorbs red wavelengths of light strongly. Sunlight entering the atmosphere has its red component absorbed, and what scatters back out, what we see, is the remaining blue and green. Neptune has similar methane content and shows a similar but distinctly deeper blue, more vivid, more saturated. The reason Neptune appears bluer than Uranus, despite similar methane content, is not fully understood. One hypothesis, an additional absorber in Uranus's atmosphere that is not present in Neptune's, selectively removing blue wavelengths and producing the slightly greener cast. What this absorber is remains unidentified. The colour of Uranus is a mystery, a mundane-seeming mystery, the precise shade of a planet, but one with no satisfying answer. If you were in a spacecraft approaching Uranus from the direction Voyager 2 approached, from the sunward direction with the South Pole facing you, you would see a nearly featureless disk growing from a point of light into an apparent diameter. The colour would resolve from blue-white to distinctly blue-green. The limb, the edge of the visible disk, would be slightly darker than the centre, as atmospheric absorption affects the longer path length of light coming from the limb. You might see, with careful observation, subtle banding, faint latitudinal structure in the clouds. Nothing dramatic, nothing like the orange and tan and white of Jupiter, nothing like the golden bands of Saturn. Pale structure in a pale disk. At closest approach, 81,500 kilometers from the cloud tops in the case of Voyager 2, the planet would fill the sky. The rings would be visible as narrow, dark arcs. You would need to know where to look. The major moons would be visible as points of light at various distances. Miranda, during the Voyager 2 flyby, was imaged at resolutions as good as 700 meters per pixel for the best covered regions. At 700 meters per pixel, Verona Rupes was visible as a sharp discontinuity in the terrain, the edge of something enormous. The coronae were visible as regions of coherent concentric structure, distinctly different from the surrounding cratered terrain, but the internal details remained at the limit of resolution. A future spacecraft, with better cameras and the ability to conduct repeated targeted flybys rather than a single pass, could image Miranda at tens of meters per pixel. At that resolution, individual geological features, fractures, ridges, pit chains, possible cryovolcanic vents would be distinguishable. The geological story encoded in Miranda's surface could actually be read. That is the difference between a snapshot and a survey. One final thought on what Uranus represents in the broader sweep of planetary exploration. The history of solar system exploration has repeatedly shown that the places we understand least are not the places we have been unable to reach. They are the places we have underinvested in visiting. Mars was poorly understood before the Mars Global Surveyor and Mars Reconnaissance Orbiter began systematic orbital mapping. Saturn was poorly understood before Cassini. Jupiter's deep atmosphere was poorly understood before the Galileo probe. In each case, the investment in sustained, systematic exploration transformed our understanding not just of the specific body, but of planetary science more broadly. Cassini did not just tell us about Saturn, it revealed the geysers of Enceladus, characterized Titan as a world with a complete methane hydrological cycle, and detected complex organic chemistry in Saturn's rings.
None of these were anticipated as major discoveries when the mission was designed. This is how exploration works. You go, you look carefully, you find things you did not expect. And the unexpected findings reshape the questions you ask. Uranus has been waiting for 38 years. Let us now think about something that connects Uranus to questions that go beyond planetary science entirely, to questions about how science itself works when the object of study is remote, expensive to reach, and yields results only over decades. The Uranus problem is in some ways a case study in the sociology of scientific priority. The planet has been scientifically identified as a top priority target for decades. The gap in our knowledge has been acknowledged repeatedly. The scientific community's consensus about the importance of an ice giant mission has been expressed in successive decadal surveys. And yet, the mission has not flown. Why? Part of the answer is structural. Large planetary missions, flagship missions in NASA's terminology, are enormously expensive. The cost estimate for the Uranus orbiter and probe, depending on the specific design and science scope, runs between $3 and $4 billion. This is not unusual for flagship missions. Cassini cost approximately $3.3 billion, the James Webb Space Telescope approximately $10 billion, but it represents a sustained commitment that must survive multiple budget cycles and multiple changes in administration. The political economy of large science projects is not straightforwardly responsive to scientific consensus. Scientists can identify priorities. They can make compelling cases for why specific measurements matter. They can publish decadal surveys that represent the broadest possible consensus of the planetary science community. But they cannot guarantee funding. The funding decision involves trade-offs among competing priorities. Earth science missions competing with planetary science missions. Planetary missions competing with astrophysics missions. Within planetary science, Mars missions competing with outer planet missions competing with lunar science. The Decadal Survey ranks priorities within planetary science, but the overall budget allocation between planetary science and other NASA science divisions is determined by different processes. There is also a timescale problem. The scientists who will benefit most from a Uranus mission, who will analyze its data for decades, are not yet in their careers. Many of the planetary scientists most excited about a Uranus mission today will be retired or gone before the mission returns its primary science. The investment is intergenerational in a way that makes it harder to sustain political momentum than investments with shorter payoff timelines. These are not criticisms of any specific decision or decision maker. They are structural features of how large science programs work in the current funding environment. Understanding them helps explain why the gap between scientific priority and funded mission exists, not because anyone is making irrational decisions, but because the incentive structures and time horizons of scientific exploration do not map neatly onto the incentive structures and time horizons of political and budgetary processes. The analogy to other long-duration investments is instructive. Building infrastructure, bridges, railways, power grids, requires commitment over timescales that exceed individual political terms. The investments that matter most for the long-term capability of a civilization are often the hardest to sustain politically, because their benefits are not visible until after the decision-makers who authorized them are no longer in office. A Uranus mission authorized today would be in orbit around Uranus sometime in the mid-2040s. The science would flow through the 2040s and 2050s. The political figures who authorize the funding would almost certainly not be in office when the science is returned. The scientific community that advocates most strongly for the mission would have partially turned over by the time results arrive. This is the nature of the commitment being asked. And yet, the investment is clearly worth making. The argument for a Uranus mission is not merely scientific curiosity. It is the argument that understanding the most common type of planet in the galaxy is foundational science that will enable the interpretation of thousands of exoplanet observations for decades. The return on investment is not just one planet's secrets. It is the calibration of humanity's understanding of planetary diversity. Now let us think about something more grounded, the specific technical challenges that make a Uranus mission harder than, say, a Mars mission or even a Jupiter mission, and how those challenges are being addressed. Power is the first challenge. At Uranus's distance, roughly 19 to 20 astronomical units, solar intensity is approximately 1/400th of what it is at Earth. Solar panels that would provide kilowatts of power at Earth provide only a few watts at Uranus's distance. This is not enough to power a capable science mission. The solution is nuclear power. Radioisotope thermoelectric generators, RTGs, convert the heat from radioactive decay of plutonium-238 into electricity. They work regardless of distance from the Sun. They operate continuously without requiring the spacecraft to point toward the Sun, and they have a proven track record across decades of deep space missions, including Voyager, Cassini, Galileo, and New Horizons. The challenge is plutonium-238 supply. The United States stopped producing plutonium-238 in the 1980s and only restarted production in 2015. The current production rate is limited, roughly 1.5 kilograms per year. A flagship mission like the Uranus orbiter and probe would require several RTGs, each containing several kilograms of plutonium-238. Building up sufficient inventory for a flagship mission launch in the early 2030s requires sustained production over the next decade. This is being addressed. The Department of Energy has been ramping up production, and planning for the UOP mission is factoring in plutonium-238 availability. But it is a real constraint that requires active management rather than passive assumption. Telecommunications is the second major challenge. At Uranus's distance, the signal travel time is 2.5 to 2.7 hours one way. This is manageable. Cassini operated at Saturn with signal travel times of 68 to 84 minutes and functioned effectively. But it requires the spacecraft to be highly autonomous and the mission operations team to plan observation sequences in advance. The data rate at Uranus's distance is also limited. Radio signals weaken with distance squared. Transmitting the same amount of data from Uranus requires either a much larger antenna, a much more powerful transmitter, or accepting a much lower data rate than missions closer to Earth. The spacecraft's high-gain antenna needs to be large enough and the transmitter powerful enough to return science data at a reasonable rate. Modern developments in communications technology, more efficient encoding, better ground receiving facilities, potentially new frequency bands, improve the situation somewhat compared to the Voyager era. But data return from Uranus will always be slower than from Mars or the Moon, and mission design must account for this. The atmospheric probe faces specific challenges related to the entry environment. The probe must survive aerodynamic deceleration from interplanetary velocities, tens of kilometers per second, to the relatively slow terminal velocity in the atmosphere. The heat shield must withstand extreme temperatures during deceleration. After deceleration, the parachute must deploy reliably. Then the probe must survive long enough in the atmosphere, which gets colder in the upper layers before warming at depth due to the lapse rate, to make the key measurements before pressure destroys it. The Galileo probe at Jupiter managed this in 1995 with 1990s technology. Modern technology allows better instruments in the same mass and power budget, and better computational power for data processing and storage. A Uranus probe designed today would be significantly more capable than the Galileo probe, even in a similar size and mass. The outer planet environment presents additional challenges. High-energy particle radiation from the magnetosphere can damage electronics. The radiation environment at Uranus is not as intense as at Jupiter. Jupiter has the most intense magnetospheric radiation environment in the solar system, but it is not negligible. Electronics must be radiation hardened. Sensitive instruments must be shielded. The spacecraft design must manage the cumulative radiation dose over years of operation in the Uranian magnetosphere. None of these challenges is insurmountable. They are engineering problems with engineering solutions, requiring careful design and testing. The technology needed exists or is being developed. What is required is the funding to apply it. Now let us think carefully about the question that underlies everything else in this discussion. Why does it matter to someone who is not a planetary scientist whether we understand Uranus? The honest answer involves several different threads. The first thread is practical in the narrow sense. Understanding ice giants better improves our ability to model and predict the behavior of the most common type of planet in the galaxy. When we eventually develop the capability to characterize the atmospheres and interiors of habitable zone exoplanets in detail, which JWST is beginning to do and future missions will extend, the interpretation of those observations will depend on having good physical models for planets across the full range of sizes and compositions. Ice giants are a significant part of that range. Studying Uranus improves our ability to say something meaningful about what a mini Neptune looks like on the inside, how it formed, and whether it could be habitable. The second thread is what might be called the intrinsic value of knowledge. Understanding the solar system, the system we live in, is part of understanding where we are and how we got here. The solar system formed from a cloud of gas and dust 4.6 billion years ago. The specific conditions of that formation determined which planets ended up where, which planets became gas giants and which became ice giants and which became rocky worlds, and ultimately which world became habitable for life. Understanding the outer planets is part of understanding that formation history. The third thread is about what systematic ignorance costs. We have now known for 38 years that Uranus is poorly understood. We have known for 38 years that our single 6-hour flyby left fundamental questions unanswered. We have continued to operate in planetary science, interpreting exoplanet data, building formation models, making claims about the structure of ice giants, with that gap in knowledge affecting the reliability of everything we do in the relevant areas. The cost of this ignorance is not easily quantified, but it is real. Every model of ice giant formation built without direct compositional data from Uranus contains avoidable uncertainty. Every interpretation of mini-Neptune exoplanet data made without a calibrated ice giant physical model contains avoidable uncertainty. Every claim about the habitability potential of ice giant class worlds made without understanding how ice giants actually work contains avoidable uncertainty. The fourth thread is the one that is hardest to articulate, but most fundamental. Exploration of the solar system is one of the few genuinely cooperative international human enterprises with clear positive returns and no obvious losers. It requires the best of human technical capability.
It advances scientific knowledge that benefits everyone. It provides images and data that have consistently demonstrated the power to inspire: the pale blue dot, the images of Titan's methane lakes, the photographs of Pluto's heart-shaped nitrogen glacier. Uranus has not had its moment yet. It has been a planet of mystery and neglect. An orbiting spacecraft, spending years in the Uranian system, returning systematic data week after week, occasionally flying past Miranda or Ariel or Titania, would produce images and scientific results that change how the public understands the outer solar system. We do not know yet what the Uranian moons look like in detail. We do not know what storms on Uranus look like over a full seasonal cycle. We do not know what the rings reveal about the system's history when examined at high resolution. These are things we will not know until we go. And we have not gone. That pale blue-green disk is sitting out there 2.7 billion kilometers away, tilted sideways, emitting almost no internal heat, wrapped in its dark, narrow rings, attended by its geologically puzzling moons, its plasma physics rotating in a helix behind it as it moves through the solar wind, its interior conducting superionic water that we cannot observe and can barely model, its seasons cycling through 42-year epochs that no spacecraft has ever tracked, its atmospheric chemistry slowly being revised by each new JWST observation, its magnetic field generating mysteries that 6 hours of flyby data cannot resolve. It is the most common type of planet in the galaxy. It is one of the least understood objects in our solar system. It is the highest priority target in planetary science, and the launch window for getting there efficiently closes in approximately a decade. What we choose to do about that is a decision being made right now. Go outside tonight, find Uranus if you can. This is possible. On a clear, dark night away from city lights, Uranus is just barely visible to the naked eye. A faint point of light, magnitude 5.7 or so, indistinguishable from a dim star unless you know exactly where to look. With binoculars, it resolves into a tiny disk, pale blue-green. With a modest telescope, you can see it clearly, a small, featureless sphere, uniform in color, giving nothing away. That is the planet, that specific point of light, 2.7 billion kilometers away. Now hold what we have established tonight about that point of light. It is lying on its side. Its rotational axis points almost perpendicular to what we would consider normal, tilted 97.77 degrees, so that its poles face toward and away from the Sun rather than its equator. Each season on Uranus lasts longer than a human lifetime. The southern pole spent 42 years in continuous darkness and 42 years in continuous sunlight before switching. Right now, the northern hemisphere is in its long summer and the southern hemisphere in its long winter. And this has been true since 2007 and will continue until 2028, and no spacecraft will be there to watch it. We do not know why it lies on its side. The most plausible explanation is a giant impact during the early solar system, a protoplanetary body roughly Earth-sized, striking the forming Uranus and knocking it over. But this explanation immediately produces a puzzle that the explanation does not resolve. That impact should have deposited enormous heat into the planet's interior. That heat should still be present, radiating outward. Neptune, nearly identical to Uranus in mass, size, and composition, radiates 2.6 times more energy than it receives from the Sun. Neptune's internal heat drives its atmospheric dynamics, its extreme winds, its visible storms. Uranus radiates almost nothing extra. Its internal heat is essentially zero by measurement. Something inside Uranus is holding that heat in, some insulating layer, some consequence of stratification, some result of the impact itself that has persisted for 4.5 billion years. We do not know what it is. We do not know what Uranus's interior looks like in detail. We know it contains water, methane, ammonia in exotic states, superionic water where oxygen atoms lock into crystalline structure while protons move freely through as conducting ions, diamond rain descending through the planet and possibly forming liquid diamond seas at depth. We know these things from inference and laboratory experiment, not from measurement. We do not know why its magnetic field is so strange, tilted 59 degrees from the rotation axis, offset from the planet's center by a third of its radius, geometrically complex in ways that no simple dynamo model produces. We think the dynamo is generated in a shallow conducting layer rather than deep in the core. We cannot confirm this.
We do not know what happened to Miranda. A moon 470 kilometers across with a cliff 20 kilometers tall, with chaotic terrain unlike anything else in the solar system, with geological complexity that should not exist in an object this small and cold. Something broke it apart, or melted it, or drove material upward from within, or all three. We have inadequate data to say which. We do not know whether Ariel, Umbriel, Titania and Oberon have liquid water oceans beneath their icy surfaces. Thermal models suggest they might. The Uranian system may contain 4 ocean worlds in addition to Miranda, potentially the richest concentration of habitable environments in the outer solar system. We have not sent the instruments needed to find out. We do not know precisely what Uranus's rings are made of. Dark material, carbon-rich probably. But the detailed composition remains uncharacterized, and a recent JWST observation found that the epsilon ring emits more thermally than models predict, which is a new puzzle rather than a resolved one. We do not know how Uranus's atmosphere behaves across a full seasonal cycle. We saw it during one specific season in 1986. We have watched from telescopes as it has changed in the decades since. We have never been there to watch systematically. We have visited Uranus once, 1 spacecraft, 1 flyby, 6 hours, in 1986. In the 38 years since, we have orbited Mars for decades, orbited Saturn for 13 years, orbited Jupiter, landed rovers on Mars, deployed probes into Jupiter's atmosphere, flown past Pluto, landed on a comet. We have built the James Webb Space Telescope and used it to observe the atmospheres of planets around other stars. We have characterized thousands of exoplanets. We have found that the most common type of planet in the galaxy, more common than any other type, is a planet with a radius between 1.5 and 3.5 times Earth's radius. Mini-Neptunes, ice giant planets, and the ice giant in our own solar system that we could study, close enough to reach, representative of this most common planetary class, we have been back to it 0 times. The 2023 Planetary Science Decadal Survey ranked a Uranus mission as the single highest scientific priority in planetary science, higher than Mars, higher than Europa, higher than anything else. Not because Uranus is the most dramatic or the most romantic target, because the gap in our understanding of the ice giant class is the most consequential gap in our ability to understand planets across the galaxy. Because understanding Uranus means understanding the context for every mini-Neptune. JWST is now characterizing, because the questions Uranus raises are fundamental, and the data to answer them does not exist. The recommended launch window opens in 2031 and closes in 2038. A Jupiter gravity assist during that window dramatically reduces the propellant required and makes the mission efficient. The next comparable window comes more than a decade later. A mission approved today would barely make the window. A mission not yet approved, without funding, without a project team, without a development program, might miss it. This is the situation. Look at that point of light. That is the most common type of planet in the observable universe, sitting in our own solar system, close enough to reach, baffling us with questions we have had 38 years and have not answered, waiting for instruments that exist and engineers who are trained and science that is ready and a window that is closing. Everything we have learned about Uranus has made it more interesting, not less. Every JWST observation has revealed new complexity rather than confirming existing models. Every improvement in telescope capability has produced new puzzles. The planet does not resolve as we look harder, it deepens. That is what the best targets do. Now think about what would happen if we sent an orbiter. It would spend years in the Uranian system. It would track the atmosphere across seasons in real time. It would fly past Miranda repeatedly at resolutions that reveal individual geological features.
It would measure the magnetic field continuously, revealing its dynamics. It would characterize the subsurface oceans of the large moons, confirming or refuting their existence. It would deploy an atmospheric probe that descends into the clouds, measuring composition and temperature and wind, and the noble gas abundances that are the chemical fingerprints of the planet's formation. And it would find things we did not expect. This is what exploration does. It finds things that were not anticipated. The geysers of Enceladus were not anticipated before Cassini. The nitrogen glacier on Pluto was not anticipated before New Horizons. The complexity of Titan's methane hydrological cycle was not anticipated before Cassini-Huygens. The surprises are not accidents. They are the natural consequence of looking carefully at places we have never seen in detail. Uranus has been waiting for its Cassini, for its New Horizons, for the mission that takes it from one 6-hour flyby to sustained, systematic exploration. The moons are waiting. The rings are waiting. The atmosphere is cycling through its 42-year seasons with no one watching. The magnetic field is tumbling in its helical magnetotail with no one measuring. Miranda's impossible cliff stands 20 kilometers tall on a world that should be geologically dead, and we have photographs of it taken from 29,000 kilometers away with 1970s camera technology. And that is all we have, and it is not enough. And we have known it is not enough for 38 years. Go inside, but take this with you. The next time you look up at the night sky, at the outer planets, at the stars, at the faint band of the Milky Way, remember that the most common type of world in the galaxy is represented in our own solar system, sitting close enough to study, telling us nothing because we have not sent the instruments to ask it. That is a choice, not a physical constraint, not a technological limitation, a choice about what matters enough to fund and build and launch. The planet cannot speak for itself. Only we can decide it is worth understanding. And the window for deciding efficiently is not permanently open.